So welcome to this session, Riemannian metrics and connections of the tutorial Riemannian geometry for scientific visualization. So far we have looked at smooth manifolds, at their tangent spaces, at additional spaces like the tensor spaces that are defined there. But we have not talked about geometric concepts like length, angle, distances. And the reason is that on a generic smooth manifold, such concepts are not defined. What you need to do so is actually a metric on the manifold to turn the manifold into a Riemannian manifold. So what is a Riemannian metric? A Riemann metric in a nutshell is a mapping in each tangent space of the manifold that takes two tangent vectors and produces a number. It is usually denoted by G and takes two vectors, say x and y. And this is usually abbreviated with this angle brackets or sometimes with a dot in between. And it defines an inner product on each tangent space. And this inner product has to have three properties. The first is that it's supposed to be bilinear. That is, you can split a linear combination in each entry. The second one is supposed to be symmetric, which means that the inner product of x and y is the same as the inner product of y and x. And the third one is that it's positive definite. So the inner product of the vector by itself is always greater or equal to 0. And it is 0 if and only if x actually is the 0 vector. And this lets us define actually the length of a vector, which is just the square root of the inner product of the vector with itself. And other geometric notions from this, like the length of curves, where we just integrate the tangent vectors along a line, and geometric notions like this. But another important geometric concept that we can do with this Riemannian metric is that we can now actually identify the dual space of a linear space with the space itself. So every finite dimensional linear space has a dual space, and this dual space actually has the same dimension, but there is no mapping between these two spaces that is in some sense singled out. If we, however, have a metric, then we have such a mapping. And this can be seen in one direction by, if you have a vector x, you can define a covector omega x by letting omega x act on y by simply taking the inner product of x and y. And by the properties of the inner product, which is bilinear and therefore linear in the second entry, this is a linear functional and therefore an element of the dual space. And one writes omega x is x flat. On the other hand, if you have a covector in the other direction, then from linear algebra we know that there is a unique vector such that this linear functional acting on y is just given by the inner product of x omega with y. And one usually writes x omega is omega sharp. So these two mappings, flat and sharp, provide an identification of the dual space, of a linear space with its dual space. And the motivation for the names comes from the musical notation, because if we look at these operations now in charts, we will see that this means that indices are actually raised and lowered. So if you're given a chart of a manifold, then we are also given a component basis in each tangent space of the manifold, because the chart determines a fixed basis for each tangent space. But we also now have a Riemannian manifold, meaning we have a metric in that tangent space. So we can take a look at all the inner products of these basis vectors, and let's denote them by G sub ij. And then we can actually compute this inner product in components. So G of x and y, or angle brackets x and y, we first can expand the x and y in their components. That is, x is xi times ei summing over all i's, and y is yj ej summing over all j's. And then since the inner product is bilinear, we can pull out xi and yj. And we are left with the inner product of ei and ej, which are now fixed numbers, because the basis is in this chart is a fixed basis determined by the chart. Which means that the inner product of x and y in components is just x, y, yj times g sub ij, and the summing over all combinations of I and j. But then, since we know that we also have a dual basis to our original basis, meaning covectors that take an element of the tangent space, an arbitrary x, and just read off their components. So omega I of x is just xi. So we can write this product as omega I of x times omega j of y times g sub ij. And then we realize that the tensor product of two one forms is just their product. So this omega ix times omega ij is actually just the tensor product of omega I and omega j. What tells us this is that actually the gij are just the components of the metric tensor with respect to the basis omega I tensor omega j. So now we can actually look at how this map that identifies a linear space with its dual space actually looks in components. So from the previous computation of g of x and y, which was just the product xi yj times g sub ij, we can actually replace yj again by the action of the dual basis on y, omega j of y. And what we see here is that this expression on the right is now just a function of y. So which means that gxy we can write as the function that maps y to gxy, and this is what we just denoted earlier by omega x. And we see that this omega x is actually a linear combination of the dual basis vector covectors omega j, but its components are actually xi times g sub ij. So we can define this to be x sub j, and then we see that the omega x is just a linear combination of omega j with the xj. And what this means is that we have effectively lowered the index xi, x upstairs I to x up downstairs j, and this is why this operation is called flat. Now this is only a notational device, but it's often really helpful to make sure that you don't mix up any indices with something where it doesn't belong. So it means that components that have the index upstairs always belong to vectors, and the components that have their indices downstairs always belong to covectors. To go in the other direction, we note that by the properties of the metric, the matrix G, which has components G sub ij, has an inverse matrix because the metric is positive definite. And we denote these components of this inverse matrix by G upstairs ij. And then we can do the same in the other direction. If we have an omega, a covector, which is just a linear combination of the basis covectors, we can set the x upstairs I to be g upstairs ij xj, and then we see that this x, which is determined by omega, is just a linear combination of the original basis vectors by these new xi, which are now computed from the components of the covector. And this is the reason why this is called the sharp operator, because it effectively raises the index of the linear combination. So this might look a bit abstract, so let's take a look at a very specific example, that of the gradient of a scalar field in the plane, which we have seen before. And there we have seen that actually on a generic manifold, where we don't have a Riemannian metric, there is no such notion as a gradient vector. All we have is the differential of a function, but this is not a vector, it's actually a covector, a linear form. It takes a vector u and produces a number in a linear way, which is usually interpreted to be the directional derivative of f in direction u. However, if we have a metric, then we know that there's a unique vector which gives the same result by just taking the inner product of this vector with u. And this is usually denoted by nabla f, and it is just the gradient of f. So what this means is that the gradient of f is just the differential of f raised. And what does it look like in components? So we've also seen before that the differential of f, df, just has the components, the partial derivatives for the basis covectors. If we now want to compute the corresponding vector, we have to raise the indices, which means we have to multiply the indices by the inverse of the component matrix of the metric. But in this case, it's easy because the component matrix of the metric in Cartesian coordinates is just the identity matrix. And the inverse, of course, is then also the identity matrix, which means that the components of the gradient vector are actually also just the partial derivatives. However, if you do the same in polar coordinates, and it's important to note that we are still on the same manifold, it's still the flat manifold, we are the plane, but we are just using different coordinates. Things change because now the matrix of the metric is actually not the identity matrix anymore, but it has an r squared in the lower right entry. And the inverse then has an 1 over r squared in the lower right entry, so we have to multiply this inverse with the components to get the components for the basis vectors. This means that the gradient in polar coordinates has the partial derivative of f with respect to r for the basis vector in direction r, but it has the component in the direction theta is actually 1 over r squared times the partial derivative of f in direction theta. So I want to talk now about a very fundamental notion in Riemannian geometry, which is that of a connection. So one of the basic problems when dealing with curved manifolds is that it is not clear anymore what it means to move things around. And when you want to do things like take directional derivatives, you have to move things around and then take the limit. And in the plane, for example, if you want to differentiate a vector field, you can move the vectors around, take the limit. That seems to be no problem. On curved manifolds like the sphere here, this is more problematic. A related problem is that of parallel transport. Again, in the plane, it seems to be clear what it means to move a vector somewhere else, and it's a parallel vector. Or similarly, what does it mean for a vector field to be constant, actually? It seems to be clear in the plane, but if you think about it on the sphere, it's not that obvious anymore. Also related is the notion of a geodesic, or straight lines in the plane. This it's clear what a straight line is, but what is a straight line on a curved manifold, or for example, the sphere? And interestingly, there is a solution to all of these problems, and this is called a connection, a very special connection which exists on Riemannian manifold, which is the Levi-Civita connection. So before I talk about the connections and the Levi-Civita connection, I want to talk about the directional derivative in Euclidean space. And the reason is that the connections are actually generalizations of this directional derivative in Euclidean space to curved manifolds. So in order to understand them, we have to understand the directional derivative in Euclidean space and what the problem is in extending them to curved spaces. So in Euclidean space, we actually just have to use multivariable calculus. Let's take a look, starting at the beginning, if you want to take the directional derivative of a scalar field. Let's say we want to differentiate a scalar field f in the direction xp, a vector x located at p, and we think of this as a differential operator. And we can write it with components of the vector x ai, and we can define a line through p in direction ai, but just defining xi equals pi plus tai, of course. And then we can define an operator d sub xp, which we apply to f, and which we want to be the directional derivative of f. And we do this in the usual way of multivariable calculus. We look at f at the location p plus ta, subtract f at p, divide by t, and let t go to 0. So this is the usual limit to calculate a derivative. But we rewrite this in analysis notation as an operator d over dt evaluated at t is 0 and apply it to the function f of p plus ta. So this is the same expression, just written in a different notation, and the reason we do this is that we now see we have to use the chain rule. And if we do that, we know that applying the chain rule to this expression yields partial derivative of x in direction xi at p times dxi over dt at t is 0 and summing over all i's. And now we realize that this derivative of xi is a rather simple one because it's just a linear function of t. So by differentiating it by t, only ai survives, and we can now move the f outside again and use this expression as an operator operating on f, and we get that the directional derivative of f in direction xp is just the linear combination of the partial derivatives with the components ai of the direction. And we also write this as applying the vector x at p to the function f. Now, if you look at these expressions, you also know from multivariable calculus that that line that we defined here doesn't have to be a straight line. It can be any line, any curve that has the same tangent vector, and we would get the same result. And this also works on a manifold. We can use a curve in a manifold and just do all these operations here, and we get a directional derivative. So there's no problem defining a directional derivative of a scalar field on a curved manifold. But if you now look at the vector field, if you want to differentiate a vector field, there you have a problem. In Euclidean space, it still works, and the reason you see in this small picture on the right is that if you look at the expression essentially at the limit again, what you do is, if you not differentiate f here, but the vector field y, that you actually subtract two vectors at two different locations. And in the plane, that's no problem, because y at p plus ta, you can just easily move it to p to the location p and subtract it from yp there, and then take the limit. And what this essentially means is that the directional derivative of a vector field in the plane is just has just the components differentiated. But it is not at all clear how this looks like on the sphere, because you can, or for example, or other curved manifolds, because you cannot just move vectors around. At least it's not obvious how to do that. And another important thing to note here is that if you differentiate the vector field in the plane, you can now actually extend this notion not from a single point to the whole manifold, to the whole plane actually, by defining it pointwise. So define an operator d sub x of y, which at the position p is just the directional derivative of a vector field y in direction x, which gives you actually an operator of a whole vector field, differentiating y, a whole vector field, in direction x, which is a whole vector field, and the result is just the directional derivative of y at each location x. Now, and if you look at it this way, we see that this actually defines an operator, which we denote by d, which takes two arguments, but these arguments are whole vector fields, x and y, and it produces a third vector field, which is the directional derivative of y in direction x at each point, which is again a vector field. And instead of writing this as d of x and y, we usually write it as d sub x of y, because it's not completely symmetric, and to make the meaning of these two arguments clear, that it's actually the directional derivative of y in direction x. But it has some nice properties. The first one is that it's actually are bilinear. So in each argument, again, you can split linear combinations of whole vector fields now, and get the same results. But in the first argument, it actually has more structure. It is even f linear, meaning you can multiply the vector field by a whole function, where the multiplication of a function and the vector field is of course defined pointwise, and you can bool out that whole function from the argument x. But, and that's the asymmetry here, in y this does not work anymore. It's not linear, it's not f linear in y, but instead the Leibniz rule holds, which is a kind of a product rule, which means that d sub x of f times y is just the vector field x applied to f times y plus f dxy. So you get this additional term that makes this second entry not linear, not f linear. And the whole point of this discussion now is that this lets us extend the notion of directional derivative to arbitrary manifolds. This is a usual strategy in mathematics, that if you cannot generalize something directly, you look at certain properties of that concepts and see if you can find something that has the same properties, and then you just consider them to be a generalization. So a connection now is abstractly just an R bilinear map, usually denoted by nabla, on any manifold, that takes two vector fields on that manifold and produces a second vector field. So this is just a map which you can define, and it is supposed to have these two properties. So first of all, it has to be R bilinear, so in each entry it has to be R linear, but in the first entry it again has to be F linear, so you want to be able to pull out the whole function from the argument x, where again multiplying a function by a vector field is defined pointwise. And in the second entry, the Leibniz rule holds, the product rule. So the nabla x of f times y is just x applied to f times y plus f nabla x y. Now this notion of a connection actually allows us to define a parallel transport, what we mean by a parallel transport on an arbitrary manifold, at least along a curve. So if we have a curve gamma from a certain interval of real numbers to the manifold, then a connection defines such a parallel operator, which is usually denoted by p, depending on gamma, from a certain parameter t0 to t1, and it is a map from the tangent space at gamma t0 of the manifold to the tangent space of gamma at t1 of the manifold. And this generalizes the notion of parallel transport in the plane. So if you do this for a plane, you get the same result as what you're used to, just pushing the vector to a different location, but it can also be now done on an arbitrary manifold. And this reverses. So from if you have such a parallel transport operator, then you can get your connection back by defining the connection nabla sub x of y at p to just be the usual limit. So you push your vector from the position gamma of h to gamma of 0, which passes through the point p, subtract the vector there at p, subdivide by h, and let h go to 0. And then this way you get the connection back. So these two notions are somehow dual. And also the next thing that you can do with this is that you actually get the notion of a geodesic, because now a geodesic is just a curve whose unit tangent field is actually parallel. So, but we still have a problem here, and the problem is that on a Riemannian manifold there might be many different connections, which means that you would get different notions for directional derivatives, different notions of what geodesics are, different notions of what constant fields are. So we apply the same strategy and look for more properties of the directional derivative and see if they narrow down our choices for a connection. And the first property we look at is called torsion, and this essentially measures how much the directional derivative commutes. So if you take the directional derivative of y in direction x and the derivative of x in direction y, in Euclidean space it turns out that this is always the Lie bracket between x and y. So one defines the torsion this way and says that the directional derivative in Euclidean space has 0 torsion. And then if you define the curvature this way, with the directional derivatives, it turns out that the directional derivative in Euclidean space has 0 curvature. And the third property is, which is called compatibility with the metric. This is essentially the product rule, just like for scalar functions. If you apply the directional derivative to the inner product of two vector fields, and then this splits into two terms, with a derivative in each term. So, of course, since we want to deal with curved manifolds, which was the whole motivation for this, we will have to drop the second property for our connection. But it turns out that if we keep the first and the third property, then we will actually get a unique connection on a Riemannian manifold. And this connection is actually called the Levi-Civita connection, after the Italian mathematician Tullio Levi-Civita. And to repeat, it is the unique connection on a Riemannian manifold which is torsion-free. This is also sometimes called symmetric, which means that the torsion is 0. And the second property is that it is compatible with the metrics. That it essentially obeys the product rule. And another good thing about this connection is that it is useful. It is actually the same as the tangential connection if you have a surface or an embedded submanifold of any Rn. If you just restrict the inner product of the surrounding space to the tangent spaces, you of course get a connection, and this is exactly the Levi-Civita connection. And then an application for these abstract concepts of connections can be found in the paper Time-Dependent Flow Seen Through Approximate Observer-Killer Fields presented at WIS 2018, where we look for connections on space-time, and space-time has the problem that it is not a Riemannian manifold, so there we have a lot of different connections, and we have to choose one in a useful way, and the way we chose there is to minimize the observed time derivative, so that the vector field that we want to explore actually is as steady as possible, and therefore easier to visualize, or also even easier to analyze. And then for doing this, we encode the connection in an observer field. For details, I refer to the paper.